In 1957, at Princeton, a 26-year-old graduate student submitted a doctoral thesis that removed a single sentence from the foundations of quantum mechanics. Not added, removed. He took out the line where the wave function collapses into one outcome. He took out the moment of choosing. What remained on the page was an equation that, when read on its own terms, said something about the word you that the word you has not yet recovered from. His name was Hugh Everett III. His advisor was John Wheeler, the physicist who would later coin the term black hole. Wheeler asked him to soften the language before defending. Everett refused. What he had written was not, in the first place, a theory about other universes. It was a theory about a word, the word that by 1957 every physicist had been treating as if it referred to a single fixed thing. The word that any person reading these lines is, almost without thinking, treating as such a thing right now. Everett's math said that this assumption, that you refers to one of you, was a habit of language, not a description of reality. What was happening on the page beneath the habit was something else. To understand what he changed, one has to understand what quantum mechanics, as it was taught, asked a person to accept. The theory was, and remains, the most precisely tested description of nature ever produced. Its predictions match experiment to 1 part in a trillion. There is no rival framework that approaches it, but at its center sits a small instruction. Before a particle is measured, the equation says, it exists in every possible state at once. After a measurement, the equation says, it exists in one. Somewhere between these two sentences, something happens that the equation does not describe. Physicists call this the measurement problem. It is, in plain terms, a hole in the very middle of the most accurate description of nature humans have ever produced. For 30 years before Everett's thesis, the standard answer to this hole had been the answer given by Niels Bohr and the Copenhagen school. The wave function collapses when a measurement occurs. Why? Because. By what mechanism? No mechanism. At what scale does a quantum system become a classical one? At whatever scale the measurement happens, what counts as a measurement? Eyes, detectors, conscious observation, something. The Copenhagen interpretation was, beneath its formality, a kind of polite shrug. Everett looked at the shrug and did the thing no one had been willing to do. He removed it. He read the equations of quantum mechanics as if they meant what they said. They said that the particle, before measurement, was in every possible state. They said nothing about a collapse. If the particle is in every state, and the detector interacts with the particle, then the detector enters every state too, and the room, and the physicist, and the planet. Nothing collapses. The wave function simply grows. Every possible outcome of every quantum event continues to exist. Each outcome is a separate branch, fully real, internally consistent. The branch experienced is the one this version of the reader is on. The other branches are other versions, in other configurations of the same wave function, equally real, mathematically inseparable from this one, and forever beyond its reach. The equation does not choose. That is what it says when the small clause is removed. This is the many worlds interpretation. It is, in the strictest reading, what the mathematics actually says. It is not metaphor. It is not philosophy. It is what the equation describes when no extra clause is added to spare the reader's intuition. In the decades since 1957, a slow shift has happened inside physics. Many worlds was at first dismissed, then tolerated, then, gradually, accepted by a growing fraction of working physicists, including some of the most precise mathematical thinkers of the late 20th century, David Deutsch at Oxford, Sean Carroll at Caltech, Max Tegmark at MIT. Not because they wanted reality to be this strange, because the alternatives kept failing. Every attempt to define collapse rigorously, to specify at what scale it happens and by what mechanism, has run into the same problem. The math does not collapse on its own. Collapse is something humans add to the equation to make it feel survivable. The equation, left alone, does not behave that way. In the picture Everett drew, choice is not something the universe performs. Every possibility that quantum mechanics permits is realized. What humans call decision, what they call outcome, what they call the way things turned out, is the experience of being on one branch and having no access to the others. The branching is not occasional. Quantum events happen continuously, everywhere, trillions of times per second in every cubic centimeter of space. Each event is a fork. The number of branches grows in a way no finite description captures. Branch upon branch upon branch, indistinguishable in number from infinity. And in some of those branches, there is a version of the person reading this who closed the page 30 seconds in. There is a version who is reading slower than this one. There is a version who has not yet been born because a chain of events 6 decades long went one way instead of the other, and the marriage that produced him never took place. There is a version who survived an illness this version did not have. There is a version who did not survive an illness this version was lucky enough never to encounter. These are not metaphors. In the picture the math draws, they are not failed possibilities. They are not what could have been. They are continuations the equation says exist. Continuations one cannot reach, because reaching them would require being the person who is them. The equation does not choose. It only describes what is, and what is, in this reading, includes them. The word you was, before 1957, a noun that pointed at one of these continuations. After 1957, in a reading of the math that has been steadily gaining ground, it points at all of them, and the one being inhabited reaches no further than a single thin slice of the structure. This is what the title of this video means. The 1957 theory did not, in the first place, change what space is. It did not change what time is. It changed what the small word you refers to. Once that is absorbed, the question is no longer whether other universes exist somewhere out there. The question is which of the versions of yourself is asking it, and what that says about the others. Everett did not live long enough to see his interpretation accepted. After his thesis, he left academic physics. He worked in defense contracting, on calculations for the Pentagon. He drank heavily. He published almost nothing else. He died at 51 of a heart attack. By his own instruction, his ashes were placed in the trash. His daughter, in a letter found after her own suicide, asked that her ashes be disposed of in the same way, so that she might find him in the next branch over. There are reasons to read this biography slowly. The man who first articulated the structure of branching realities lived a life that, in this branch, ended in a particular kind of silence. The interpretation he proposed is now taught in graduate physics. Whether there is a branch in which Everett was celebrated in his lifetime, the math does not say with certainty. It only says that the absence of such a branch is not what one would expect from the mathematics taken at face value. Many worlds is only one of the doorways. To understand why this matters, why a physicist in 2025 might read Everett's thesis and feel less like he was reading a curiosity and more like he was reading the first sentence of a book that has been writing itself since, one has to look at what else the math has done while no one was watching. Begin with the universe itself. Begin with the fact that this universe should not exist. In the 1970s, as physicists started running the numbers on what makes a universe like ours physically possible, something uncomfortable surfaced. The values of the fundamental constants, the strength of gravity, the strength of electromagnetism, the mass of the electron, the cosmological constant, are not arbitrary in the universe observed. They sit, each of them, in a narrow window. If gravity was stronger by 1 part in 100 million, stars would burn out in a few thousand years or never ignite at all. If the ratio between electromagnetism and the strong nuclear force shifted by a few %, atoms would not form. If the cosmological constant, the energy density of empty space, varied by 1 part in 10 to the power of 120, the universe would either have collapsed before galaxies could form or expanded so quickly that matter never gathered. 1 part in 10 to the power of 120. The number is, in any ordinary sense, not a margin. It is a miracle, or it is a clue. There are exactly 2 ways to explain a number like this. One is design, that someone tuned the dial. This is not physics. The other is selection, that the dial was set many times, across many universes, and the one universe in which the tuning landed in the habitable range is the one in which there are creatures who can now sit in chairs and ask why the tuning landed where it did. What this argument does, on its own, is not prove the multiverse. It locates the version of you that is asking the question. It places that version inside a much larger pool of arrangements, most of which contain no version at all. The question is no longer whether the dial was rolled many times. The question is why this roll, with these constants, with this brain in this chair, is the one performing the asking. By the end of the 1970s, physics began to offer a mechanism for how more than one roll could occur. In 1979, a physicist named Alan Guth was working on 3 unrelated problems with the standard model of the Big Bang. The model itself was extraordinary. It accounted for the expansion of the universe, the cosmic background radiation, the relative abundance of hydrogen and helium. But it had 3 gaps no one had been able to close. Why is the temperature of the universe so uniform across regions that, according to the model, had never been in contact? Why is space, as far as instruments can measure, perfectly flat, when even the smallest curvature early on should have been amplified into a massive one by now? And where are the magnetic monopoles that grand unified theories predicted the early universe should have produced in enormous quantities? Guth's answer to all 3 was a single mechanism. In the first fraction of a second after the Big Bang, a period of time so short it has no name in ordinary language, 10 to the minus 36 seconds, the universe underwent a phase of exponential expansion. Space stretched faster than light. A region smaller than a proton inflated to the size of a grapefruit. Then this phase ended, and ordinary expansion took over. This is inflation. It solved the 3 problems at once. Regions that had been in contact before the phase were stretched apart. Uniformity preserved. Curvature was flattened the way the surface of a balloon flattens as it inflates. The monopoles were diluted to 1 per observable universe, which is why none have been found. Inflation became the leading cosmological model. It predicted specific patterns of temperature fluctuations in the cosmic microwave background. And when the WMAP satellite in 2003 and the Planck satellite in 2013 mapped those fluctuations, the predictions held. But inflation, once it begins, does something its inventors did not plan for. The field that drives it, the inflaton field, does not shut off everywhere at once. It shuts off in patches. In one patch, the field decays. Energy converts into matter, and what we call a Big Bang occurs, producing a universe. In the surrounding regions, the inflation continues. In those regions, more patches stop and produce more universes, and so on, forever. This is eternal inflation. André Linde, who developed one of the most complete versions of the theory, spent years trying to construct a model in which inflation did not produce a multiverse. He failed. The multiverse in this picture is not something added. It is what inflation does when allowed to run. The result is an infinite expanding foam of bubble universes, each one the product of inflation stopping in a particular region, each one causally isolated from every other. And this is the part that connects back to the fine-tuning problem. Each one, potentially, with different physical constants. The mass of the electron different, the strength of gravity different, the cosmological constant different. In the overwhelming majority of those universes, there are no stars and no atoms. In the small fraction where the constants fall in the habitable range, there are people. The constants in this universe are not, in this picture, designed. They are sampled. The dial was rolled many times. This is the only roll on which a sentence like this one could ever be read. This compounds, in a particular way, what Everett's math began. Inflation, taken seriously, places this universe in a vast pool of others. Many worlds, taken seriously, places the version of you in this universe in a vast pool of other versions. The two pictures arise from different problems in different decades. They do not require each other. They both produce a multiverse. And again, on each path, the same question returns. Not whether the others exist. Which of them is the one reading? There is a third path. In the 1980s and 1990s, theoretical physicists developed string theory as an attempt to unify quantum mechanics with general relativity. The two theories that together describe everything observed, and yet are mathematically incompatible at the deepest level. The proposal was that the fundamental objects of physics are not particles, but tiny one-dimensional strings, vibrating in higher dimensional space. Different vibrational modes correspond to different particles. An electron is one mode, a quark another. Gravity emerges as a particular vibration. The math was elegant. It was finite where quantum field theory was infinite. For a time, it was considered the best candidate for a theory of everything. Then the problem appeared. String theory required extra spatial dimensions beyond the three observed, and the extra dimensions had to be compactified, folded up too small to detect at the energies available to any instrument. When physicists tried to calculate exactly how these dimensions can fold, they found not one solution, not 10, approximately 10 to the power of 500. Each solution corresponded to a different set of low-energy physical constants. Each was a different possible universe, with different values for everything. This was not what anyone wanted. The hope had been a unique theory of everything that explained why the constants are what they are. Instead, the math produced a landscape of every possible variation, and our universe sat in one tiny region of it. Leonard Susskind, one of the founders of string theory, eventually argued that the landscape was not a failure, but an explanation. The constants are what they are because life is possible only in the region of the landscape where they are. The math did not give a unique universe. The math gave a sample space. When inflation and the string landscape are combined, the picture sharpens. The inflaton field, as it drives expansion in different regions of the cosmic foam, can settle into different vacua, different points on the string landscape, each producing a bubble universe with different physics. Every configuration the landscape permits is realized somewhere. The configuration in which a person sitting on this branch, in this bubble, with these constants, can wonder which other configurations were realized is this one. What stands after this is again the same question, not whether the others exist, which of them the reader is, and why this one. The math is silent on the second part. There is a fourth doorway, and it is stranger still. In 1997, the Argentine physicist Juan Maldacena published a paper that has since become the most cited in the history of theoretical physics. He demonstrated that a theory of gravity in a three-dimensional space is mathematically equivalent, not analogous, but exactly equivalent, to a quantum theory without gravity operating on the two-dimensional boundary of that space. Every event in the three-dimensional bulk can be described fully by a theory living on its surface. This is the holographic principle. It implies, if taken seriously, that the three dimensions of physical experience are not the fundamental reality. They are projected. The substrate is a two-dimensional quantum system encoding everything. The volume one walks through is a kind of rendering. The amount of information in any region of space, the math shows, is proportional not to the volume of the region, but to its surface area. This is not metaphor. This is what the equations of general relativity, combined with quantum mechanics, say. If holography is correct, then the question of other universes shifts again. The two-dimensional boundary might support many different three-dimensional bulks, different geometries, different spacetimes, different universes, all encoded as different solutions to the same boundary theory. The version of you in this volume is one rendering. There may be others in geometries the same substrate also permits. A separate idea, developed by Maldacena and Susskind together, suggests that the very fabric of space is woven from quantum entanglement. Entangled particles in this picture are not just correlated across distance. They are connected by microscopic wormholes, structures in spacetime that arise from the entanglement itself. If spacetime is a product of entanglement, and entanglement is a quantum phenomenon, then spacetime is a quantum object, and quantum objects exist in superpositions. The universe, at the level of its full wave function, may exist in a superposition of geometries, a superposition of spacetimes, each one corresponding to a different version of itself. The reader on this branch, in this rendering, in this bubble, in this configuration of constants, is one cross-section of all of that. The other cross-sections do not pause to be examined. They continue, on the maths terms, in their own. 4 doors. None of them was opened in order to find what was behind them. Inflation was an attempt to fix 3 unrelated problems with the Big Bang. Many worlds was an attempt to remove a clumsy clause from quantum mechanics. The string landscape was the unwanted byproduct of an attempt at a theory of everything. The holographic principle was discovered while studying the boundaries of black holes. Each of these efforts began with a different question. Each of them produced, as a residue, the same answer. The math does not appear to want one universe. It appears to want many, in different senses, by different mechanisms. And what no one has yet succeeded in doing, in 7 decades of trying, is finding a way to write down any of these frameworks without the conclusion appearing in the residue. There are skeptics, serious ones. The most common objection is that none of this is testable in the way other physical theories have been. The bubble universes of eternal inflation are causally separated from ours. Nothing crosses the gap. The branches of many worlds are, by definition, inaccessible from each other. The string landscape, in most formulations, predicts no specific universe and so cannot be falsified. The holographic principle has produced mathematical predictions about black holes that match independent calculations, but it has not yet been confirmed by direct experiment in the way that, say, gravitational waves were confirmed. The objections are honest. They have force. But the defenders point out something that is also honest. Physics accepts entities it cannot directly observe whenever those entities are the unavoidable consequence of theories that are confirmed by other means. Quarks cannot be seen. The interior of a black hole cannot be seen. Dark matter has never been detected directly. These are inferred, required in fact, by the math of theories that match observation everywhere else. Inflation is confirmed by the cosmic microwave background. Inflation, taken seriously, produces eternal inflation. Eternal inflation produces bubbles. The fact that the bubbles are far away is a consequence of physics, not a sign that the math is wrong. The same logic, in different forms, holds for the other three doorways. There are also pieces of observational evidence that do not, on their own, prove anything, but do not vanish either. In 2008, a NASA team led by Alexander Kashlinsky reported that galaxy clusters across billions of light-years appeared to be moving, all of them in one direction, a bulk flow that no structure inside the observable universe could explain. The team proposed that the clusters were being pulled by the gravity of something outside the observable horizon. In 2015, a team at University College London, led by Stephen Feeney and Matthew Johnson, searched the cosmic microwave background for signatures of bubble collisions, places where another universe might have brushed against ours in the early moments. They found 4 candidate spots with the right geometry and statistical properties, including the well-known cold spot in the southern sky. None of these is proof. They are all consistent with simpler explanations. They are also consistent with what would be expected if eternal inflation produced other universes, and one of them, billions of years ago, came close enough to leave a mark. What needs to be held in mind when all of this is laid out together is the structure of the situation, not one path, 4 paths, begun in different decades by different people in answer to different questions, with no coordination among them, all of them landing in the same room, each by its own door. This is the kind of pattern that, in any other domain, would be called a discovery. The reason it is not yet called that in physics is that the discovery, if it is one, is uncomfortable in a way physics has not had to confront in a long time. It is uncomfortable because what is being discovered is not a new particle, not a new force, not a new constant. What is being discovered is that the noun you is the wrong noun. The thing the word points to, if any of these frameworks is even approximately right, is not one of you. It is a region of a larger structure, and the structure was there before the word arrived. Once that is said, the implications can be touched. Free will, in the picture Many Worlds describes, is a different kind of concept than the one most people carry around. The question is no longer, what will I choose? The question is which branch I find myself on after the choice. Every option the wave function permits is taken. The branching is constant. What is experienced as decision is, in this picture, more like a selection of which version of oneself one ends up being. Whether the language of agency survives this redefinition is a question philosophers are still working through. The math is indifferent to the question. Death, in this picture, is also a different kind of event. In some branches, a person survives what kills him in others. In some branches, the heart attack that ended Hugh Everett at 51 did not occur, or occurred and was caught in time. This is not immortality. There is no continuous thread of subjective experience that crosses the branches. It is something stranger. It is a permanent dispersal of versions, most of which will end and some of which will continue. And the one who reads this is, by definition, on a branch where the reading is happening. The branches in which it is not happening are also real. They are simply not this one. This is the part that is hard to read without flinching. It is also the part that the math, in its indifference, does not soften. There is no rule in quantum mechanics that says only one branch counts. There is no equation that privileges the version of you reading these words over any of the others. The privilege is local. It is the privilege of being the one who happens to be here. And this is the place to return, finally, to the line that began this. Everett's 1957 theory changed what the word you means. It did not change it through philosophy. It did not change it by argument. It changed it through equations that, when followed where they lead, dissolve the assumption built into the word, that you refers to a single, fixed, continuous thing. The math, on its own, says that the word was, the whole time, a label for one cross-section of a far larger object. The label is not wrong. It is local. It marks the one slice that is the slice of the reader, and it cannot reach the others. What physics has done, in the 7 decades since, is not soften this conclusion. Physics has produced 3 more frameworks that arrive at related versions of it through entirely different doors. Inflation, taken at its math, opens a foam of bubbles. The string landscape, taken at its math, opens a sample space of physical laws. Holography, taken at its math, opens the possibility that the volume of experience is itself a projection from somewhere else. None of these requires the others. All of them dissolve, in their own way, the picture of one isolated universe containing one isolated version of the reader. The picture that survives in each is a picture in which you is one configuration of a much larger structure. This is what was on Everett's desk in 1957, when his advisor asked him to soften the language. He refused, and the language stayed sharp, and 7 decades of physics that did not set out to confirm him have moved slowly and through unrelated paths in his direction. The story of physics for the past 400 years has been a story of widening. The Earth was the center of everything until it wasn't. The Sun was the center of everything until it wasn't. The galaxy was the only one until it wasn't. The observable universe was the whole of what exists, until that began to look provisional too. Each widening has cost the human asking the question some part of what he believed about his own place. None of them has been welcome. All of them have been quiet and accurate and irreversible. What is left on this branch, on this slice of the structure, is one version of a creature reading one set of words about an idea that, if it is right, means there are others reading nothing, and others reading something different, and others who never reached this sentence because the conditions for arriving here did not hold in their region of the wave function. The one who did is the one who is here. And the question that began at Princeton in 1957, the question that the equations have spent 70 years circling, is the question of what to do with that. There is no instruction. The math does not offer one. It offers only the picture, and the picture is what it is. Hugh Everett went home, drank too much, and stopped publishing. The interpretation he proposed kept growing without him. Somewhere, in a branch where the math read differently, or the year was earlier, or the advisor was less polite, None of this is true. On this branch, on this version, in this configuration of the wave function, it appears to be. The equation does not choose. What it leaves, in place of the choosing, is this. The word you is not what it was before 1957. That, at least, is what the equation says when no one asks it to comfort us.